Nowadays, most people explain magnetic force using Maxwell's theory, which was a summary and development of the thoughts of 19th century scientists like Gauss, Faraday, and Ampere. As an alternative, Edward Purcell tried to explain electromagnetic force relativistically. Ampere's law states that electric current produces magnetic field around it. In classical electromagnetic understanding, this is often thought that the space around the electric current contains magnetic field. Hence, the magnitude and direction of magnetic field at some point is the properties of the space at that point, which is stated by Biot-Savart's law as vector summary of electric current components around it. This law states that magnetic field produced by current fraction in a conductor at a point around the conductor is expressed in this equation.
Here is a picture of magnetic fields created by a long wire with constant electric current. In this picture, the magnetic fields below the wire are towards picture plane as described by right-hand rule. Positively charged particle below the wire moves to the left and feels magnetic down force F equals Q times B times V, since B is perpendicular to V. According to Maxwellian understanding, magnetic field B is a property of the space around the wire, and it's not affected by V. If the particle is used as reference frame, then the wire becomes the moving part. The stationary particle feels downward magnetic force like before. Now we add another wire below the particle with the same direction of electric current but physically move in opposite direction to the first wire. In the place where the particle resides, B equals 0 because the second wire produces magnetic fields with the same magnitude but opposite direction to the first wire. Nevertheless, the second wire gives down force as much as the first, thus the resultant force becomes twice. From here on it can be concluded that the idea about magnetic fields that fill the space is not adequate to explain electromagnetic phenomena. Now we will try to determine the speed reference. Lorentz force states that an electrically charged particle moving in a magnetic field will get magnetic force F equals Q times B cross V. If the charged particle is stationary to the wire, no magnetic force is received. If the source of magnetic field is a long wire with constant electric current, then V is measured relative to the wire. Note that inside the wire there are electrons which are moving relative to the metal atoms in the wire. The equation above shows that if an electrically charged particle is stationary to the wire, it will not get magnetic force, no matter how fast the speed of the electron inside the wire. If the wire is moved in the same speed but opposite direction with the electrons, then the charged particle is stationary relative to the free electrons inside the wire, but moving relative to the metal atoms of the wire. Then it is shown that in the particle's reference, movement of metal atoms produce magnetic force, while movement of electrons doesn't have direct effect on its own. Nevertheless, electrons' movement can neutralize metal atoms' movement if both of them move in the same speed and direction, because the current would be zero. Electron can even reverse the direction of the force if it's moving in the same direction with the metal atom but with higher speed. We can make a table showing the force experienced by the stationary test particle in various velocities of both positive and negative particles in the wire. It's assumed that all positive particles have uniform velocity. Negative particles have uniform velocity as well. The first table shows the value of electric current, which depends on the difference of velocity between positively and negatively charged particles in the wire. If they are the same, then the electric current as well as magnetic field will be zero. The second table on the top right shows the velocity of the wire relative to the lab frame. It's the same as the velocity of the positively charged metal atoms in the wire. The third table on the bottom right shows the force exerted to the test particle. It's simply the multiplication between the cells in the first table and the corresponding cells in the second table. There are some patterns identified in the third table. Positive values mean that positively charged test particle will be pushed away from the wire, while negative values mean it will be pulled towards the wire. Zeros mean that the test particle doesn't experience any force. It happens when the current is zero, or the speed of the wire is zero. There are more positive values than negative values. Thus, if the velocities of particles in the wire are random, it's more likely for the test particle to be pushed away. When the electrons in the wire are kept stationary, the Lorentz force to the test particle is proportional to the square of wire's speed.
The difference between the motion of positively charged particles and negatively charged particles to the force exerted to test particles can be shown by measuring the voltage produced at the bottom of conductive bodies below two similar systems. I'll call this electrodynamic balance. There are two fundamental differences between positive charge carrier, in this case, metal atom, and negative charge carrier, which is electron, inside a wire with electric current. They are charge sign and mass. In the prepared experiment, we will examine the effect of charge sign and mass of the electric current producers to the magnetic forces that they produce. This can be done by replacing electron as the current producer with ions with various charges and masses, while the metal wire will be replaced by a container filled with electrolyte solutions. Here's the sketch of the experimental setup. I think this is so simple that anyone can replicate it.